Hey everyone, it's Bradley Bush with an algebra video. Today we're talking about modeling exponential growth and decay, and here is our to-do list. We have, first off, quick model overview for those who might need a little refreshing on your exponential growth or decay models. Then we'll talk about three classic types of problems. I see these three types of problems in every algebra textbook that I've ever taught from. And then after we discuss those three types, we'll actually do three examples, one of each of the types. Let's start. Here's your quick model overview. All right, here's the model. So a quick overview of the model. A0 is the initial amount, meaning if you start and you're growing bacteria in a petri dish and you start with 20 bacteria in your dish, A0 would be 20. After time 0 and when time starts marching forward, at any time t, A or F right here, that would be your amount at the current time, whatever that time is. Your variable in the equation is t. We have E. E is the natural exponential function. So this is an exponential growth or decay model with base E. And K is your growth constant. If the growth constant is positive, it's a growth constant. If the constant is negative, it's a decay constant. Meaning you've got a decay model. If K is negative, it's a decay model. If K is positive, it's a growth model. And a graph would look just like this. You would start at some initial population value, and then as time marched on, you would grow, or you would start at initial population value, and as time marched on, you would decline. Your population would decline. If you want to see a little bit more about specifically this model, check out my video on what is an exponential growth or decay model in my algebra playlist. The three major types of modeling problems I see as an instructor. First one is the question, we'll say, build a model. They'll give you information. They say, build this model that describes this data. Second type of equation you'll see is they will give you input, and then they'll ask you for the output. So you are looking for the output. They give you the input, they ask you for the output. This is probably the easiest of the three types by far, because this, you're just plugging in a number into an equation. Evaluating, that's all you're doing there. The third major type of equation or problem is you're given an output and they'll ask you for an input. This is a little bit more difficult than the type number 2, but we can still do it. So they give you the y value and you've got to find the x value. All right. Let's try a problem. So this problem deals with the first type, which is build a model. So it says build a model that describes U.S. population data from 1970 to 2010. So this is actually U.S. population data from 1970 to 2010. Where do we start? Well, we need time equals 0 because we need to have, we need to know what A0 is. What's the initial population? So we find an initial population by deciding where we're going to place t equals 0. So if we let t equals 0 be 1970, then that means that t equals 0 is 1970, 1980 is t equals 10, 1990 is t equals 20, 2000 is t equals 30, and 2010 is t equals 40. Another reason that they like to change these, because now my x, or my input, is going to be this right here, the t, into my model, and my output will be the US population in millions. Another reason that we like to use t equals 0 for 1970 or t equals 10 for 1980 is because if you're actually graphing this, and say you've got a graph, your y is the population in millions and your x is the time, say in years. If we want to graph 1980 in 226.5 million, if we're starting with 1, 2, 3, we've got a really long time before we get to 1980. So what happens to all of this dead space in the graph? It's just wasted. It's really poor form. So that's another reason we like to say we're going to start this whole thing at t equals 0 and then move on from there. So then our graph is exactly what we want to see, which is starts close to the y-axis and then moves forward from there. So now we've set our t, so we've kind of changed our input variable. We know what it is now. The initial population, which is A0, is just the US population at time t equals 0. So we've found A0. A0 is 203.3 million. We need A0 and K. Those are the two things we need for the model, right? Because E, that's just a natural exponential, and T, that's just our variable, so it stays. It never changes. So the two items we need, the two constants we need, are A0 and K to be able to specify our model. So we just found A0. Again, A0 is just, it kind of looks like an Easter egg. A0 is just the data point at time t equals 0. So at t equals 0, what is our population size? 203.3 million. So now, how do we find K? Well, let's start by updating our model, because we know that A0 is 203.3. We need to find what K is. What do we know? We know we have some data, right? We have all of that data right there that I just circled. So why don't we just pick a time and a US population and plug them in? Because if we did, that would really be awesome. We would all we would be left with is an unknown, would be K, and then we could just solve for K. So we know, for example, t equals 10. At t equals 10, what is the population? The population is 226.5. We just read that off of here. I guess I should circle a 10. So we know that 10 years after 1970, the US population is about 226.5 million. So our model would kind of look like this. Y equals 203.3 e to the k and t. So the y and the t, we are going to plug those in. This right here, sorry, not the k and the t, the y and the t, we're going to plug those in. The f of t, that's going to be our y. So how about we plug in the point 10, 226.5, 10 and 226.5, and then we solve for k. That'll give us exactly what we want. So the y is 226.5 equals 203.3 e to the k, which we don't know, but we'll soon know, and 10. Awesome. Now we solve for k. We have our equation. I'm going to copy and paste it down here so we can move a little bit faster. We need to isolate the exponential, so I'm going to do that by dividing away 203.3. That's great because the 203.3 cancels on the right side of the equation. And what are we left with now? We're left with 226.5 over 203.3 equals e to the k times 10. Well, we need to get the k and the 10 out of the exponent. A great way that we have done this in the past, if you've been watching my algebra videos, is we've taken the ln of both sides. So why don't we try that here? If we take the natural log of both sides, our log rules allow us to take the k and the 10 out front. Perfect, because the e and the ln cancel. So we're left with the natural log of 226.5 over 203.3, and this equals k times 10. So you can imagine we only have one more step, and that step is divide by 10. So that gives us k equals 226.5 divided by 203.3, the natural log of that, all divided by 10. So right here, well, I should probably tell you what that is. If you put that into your calculator, it would look something like 0.0108 approximately. All right, here's the calculator. Let's plug in our value for k and see what we get. So we're going to have open parentheses because we have a numerator and a denominator. Then we'll have ln. We have 226.5 divided by 203.3, close parenthesis, another one divided by 10. And we get 0.0108. So that's what we're going to use. Now, we should probably update our model. So instead of having a k there, we know what we have for k. So let's plug it in. 0.0108 times t. And here we go. We're done. We've found our model. We could plug in any time t in years starting at 0 up to 40 and get an estimated amount according to our model of the US population at that time. And I played around with it a little bit, and it's actually really accurate. It's surprising how accurate this model is according to the data that we have from the US population. So that's kind of cool. If you want to play around with it, you can Google US population at, say, 1980, 1985, and plug in the appropriate number for t and see how close you are. I think you'll find you're really, really close. So that's kind of fun. All right, so here's our second of the 3 types of classic questions. This one is, we are given an input and we've got to find an output. So again, remember this was the easiest of the 3 types. So that's awesome. We always like the ones that move quickly, right? So it says, now that we have a model, what is the US population in 1995? So 1995, what is that in terms of our t? If we scroll up to where our t's were, 1990 was 20, 2000 was 30, so 1995 would be 25. So t is 25, so all we do is plug in t equals 25 into our function. And that's what we're going to do. 25, and there's our function, and I'm going to put 25 right here. Let's see what we get. So we have 203.3 times e to the parenthesis 0.0108 times 25. $26.32. We'll round it off at the 100th place. So that gives us approximately 266.32. How close is that to our actual data? 266.32. If we look at our data, 1990 we had 248, 2000 we have 280. So we're saying in 1995 our model says that we have 266.3. That looks very plausible. And if you Google what's the US population in 1995, you'll find out that it's really, really close. So that's great. We have finished our second type, so you can see why the second type of classic problem, they give you an input and you just find what the output is super easy, because all you're doing is, it's plug and play. All you're doing is plugging in the value into the model that you already have. If they don't give you the model, then you've got to build the model first like you did in part A, and then you plug and play for part B. So part C. So here we have, they give us an output and we find the input. So in other words, they give us in our situation, they're going to give us the amount, the population, and they wanted us to find the year. And if we look at our question, that's what they say. They say, when does the US population reach 275 million? If we looked at the actual data, 275 million. Well, it's going to be after 1995 because that's 266, but it's going to be before 2000 because that's 281. So we're guessing somewhere in the late 90s. That's our guess, just looking at the data. But we don't know exactly, but we can find out. So that's what we're going to do. So what we do is we take our model that normally spits out populations, and we fix the population, and we solve for time. 203.3 e to the 0.0108 times t. So now what we're going to do is we're going to solve for t. So that's a lot like solving for k, the constant. So let's divide both sides by 203.3. The 203 cancels on the right side of the equation, and we're left with 275 divided by 203.3 equals e to the 0.0108 times t. And again, we're going to use our take a natural log of both sides trick, because e and natural log cancel each other out. They're inverse functions. And the wonderful thing is this comes out in front, the constant k times t, which is what we want out front because we want to solve for t. So that gives us the natural log of 275 divided by 203.3, and that equals 0.01. That's a terrible 0.01. 08 times t. Now, final step, divide away the 0.0108. And we get our t. Whoops. Which is 275 divided by 203.3, the natural log of all that, all over 0.0108. And what is that when we plug it into our calculator? Well, let's see. Natural log 275 divided by 203.3 divided by 0.0108. 27.97. 27.97 years from 1970. So what is 27.97 years from 1970? What does that give us? Somewhere in late 1997. So somewhere in late December, the U.S. population will hit 275 million. And again, if you look it up, if you Google U.S. population in December 1997, you'll see it's just below 275. And if you look at it in January of 1998, you'll see it's above 275 million. So that's a really good estimate. It's a really good estimate. And that's it. Those are the three main types, three classic types of problems. Again, the three types of problems that you'll see We've done all three of them. We built a model. We were given input and we were asked for the output, and we were given output and we were asked to find the input. Hope this helps. Modeling is actually a really fun thing to do because you are able to apply your math to something that is interesting. And hope you enjoyed it. Have fun modeling.